In the last couple of segments, we introduced the concept of nucleophilic substitution reactions, where we replace a leaving group that's bonded to a carbon with a nucleophile. We talked about both the SN2 reaction mechanism, which is the one-step reaction mechanism where the nucleophile attacks from the so-called back side at the same time the leaving group leaves from the front side. And then we proceeded to talk about the other reaction mechanism called an SN1 reaction mechanism, where the first step of the mechanism is that the leaving group leaves to give a carbocation. Now what we're going to look at is a permutation of the SN1 reaction at an allylic carbon. And first off, a reminder of what we're referring to when we talk about an allylic carbon is we're referring to the carbon atom that is separated by a single bond from an alkene group. So in the molecule that we have drawn here, our allylic carbon is the carbon atom that is located right here. So it is possible that you will run into situations where the allylic carbon is bonded to a leaving group. Remember that the leaving group is an electronegative atom that results in that carbon being positively polarized. So here our chlorine is our leaving group, the electronegative atom that causes this carbon to be positively polarized because the chlorine is pulling electron density away from that carbon. Also, this carbon-chlorine bond is a relatively weak and easily broken bond. So we're going to look at what implications having an allylic carbon has on the SN1 reaction and the mechanism that we need to look at here. So let's go ahead and get started with that. We'll use this problem as our example to illustrate SN1 reactions at the allylic position. So the situation where there is SN leaving group bonded to the allylic carbon. So let's go ahead and redraw that structure that we had just a moment ago. So I'm just redrawing that. And then we had it reacting with CH3SH methylthiol because the S causes this to be a so-called thiol group. And we're going to predict the SN1 mechanism that would take place here at this secondary carbon. So the secondary carbon that's bonded to the leaving group, which typically leads us to think that the reaction could undergo an SN1 or an SN2 mechanism, since in the earlier segments we talked about SN2 mechanisms are most favorable at primary carbons, SN1 mechanisms are most favorable at tertiary carbons, and secondary carbons are switch hitters. They can go either SN1 or SN2 depending on the exact reaction conditions. So here the problem is telling us to do an SN1 mechanism for this. So let's go ahead and get started with this and see what twists and turns result in this mechanism as a result of having the leaving group at the allylic position. So step number one, same as what we've seen all along for an SN1 reaction, and that is that the leaving group leaves or breaks away in this rate determining step. So this is the slowest step of the mechanism always, because we're going from a relatively stable starting material into a relatively unstable intermediate, a carbocation. And so that's going to make this step energetically unfavorable. It's going to have a very high energy barrier relative to the other steps. And so we'll show this formation of our carbocation intermediate here, which is always the first step of an SN1 reaction mechanism, the leaving group leaves. Just to emphasize, this is our bottleneck step. It is the slowest step, and therefore it's going to determine the overall rate of the reaction. I'm putting RDS there for rate determining step. We show the electrons from the covalent bond coming over and going on to the chlorine, and we will go ahead and write out what results from this step. So I'll have a positive formal charge right here at this carbon, and to counter that we'll have our chloride anion that results from breakage of that carbon-chlorine bond. And now at this point, the second step of the mechanism, as you learned it before, was if you create a secondary carbocation, you should look for a carbocation rearrangement. The carbocation rearrangement takes place because by induction, a tertiary carbocation is more stable than a secondary carbocation because the tertiary carbocation has more alkyl groups which donate electron density over toward that positive formal charge, thereby stabilizing it. In this case, though, we have our carbocation at the allylic position. And when the carbocation is at the allylic position, it is possible to do resonance here. if we were not at the allylic position, there would be no opportunity for resonance. But here there's the opportunity for resonance. And remember that resonance is a stronger factor for stabilizing molecules than is induction. And so in this situation where we have the carbocation at the allylic position, we want to do resonance rather than a carbocation rearrangement, because the resonance is what's going to be the major factor to stabilize the molecule here. And therefore, the carbocation rearrangement that improves the induction is not going to be relevant here. It's not going to be necessary. So our second step of the mechanism here, where we're doing a reaction at the allylic position, where there's a leaving group there at the allylic position, is that we're going to make sure that we are showing resonance. And resonance technically is not a step of the mechanism. Rather, it's something that is going to happen automatically. There's no energy barrier to it. Remember that resonance is implying that the actual structure here is not the structure that we've shown up top, nor is it the resonance structure we're showing on bottom. Instead, it's essentially a weighted average or hybrid of the possible resonance structure. So let's take a look at the resonance that we can draw here. I'm going to show my resonance arrows in green. So remember that resonance is going to be shown by moving the mobile electrons, that is the pi electrons or the lone pairs, closer to that positive charge. So we can move those over to here to move our carbon-carbon double bond. So we'll move our carbon-carbon double bond over to right here. As a consequence of that, the carbon that was originally our carbocation up top now has a complete octet, so it is no longer a carbocation, because remember that there had to be a hydrogen here to start with. Still a hydrogen here now, so that carbon has a complete octet. It's now going to be the carbon at the left-hand end of the molecule that is lacking an octet, and therefore will take on the positive charge. We can start off with CH2 here, filling the octet for that carbon. We still have CH2 here at the end, but now since there's no double bond there associated with that carbon has to have a positive formal charge because there's only 3 covalent bonds and no lone pairs. So I'm just going to put, for emphasis here in brackets, my 2 resonance structures. And to emphasize this point, there will be no carbocation rearrangement. I'm going to make a little note here that resonance is greater than, and make a note here that resonance is greater than induction. So when there is resonance possible to stabilize a molecule, that resonance is going to be what we look at as our stabilizing factor, because resonance is the most important factor for stabilizing the molecule over induction. So I'm putting a gold star there on resonance to emphasize that we want to remember that resonance is the important factor in stabilizing the molecule when we have to compare resonance and induction. So here, since we have resonance, there is no need for rearranging the molecule to improve the induction situation. So therefore, don't do a carbocation rearrangement. We only rearrange the carbocation if we are in a situation where we can't do resonance. Here we can do resonance, therefore we are not going to rearrange the carbocation, because rearranging the carbocation would just make a secondary carbocation into a tertiary, which would improve the induction, but induction is not as strong of a force as resonance. We can think of resonance as being the stronger force because resonance allows us to fully share the positive formal charge over multiple atoms. As we're seeing with our 2 resonance structures for the allylic carbon, we're sharing that positive charge over 2 different carbon atoms, hence each carbon atom only has to bear essentially half of the burden of that formal charge. On the other hand, with induction, we're just lightly polarizing bonds to somewhat sort of share the electrons and move them about, but we're not fully able to distribute that formal charge over multiple atoms. Resonance fully distributes the formal charge over multiple atoms, making it a stronger force here than induction. So since we have resonance going on here, we do not want to do a carbocation rearrangement. So whatever you do, don't try to move a hydrogen over or a methyl group over in a 1-2 shift. It's not necessary. Resonance is the king of the castle here. All right, so we had the leaving group leave. That created our resonance stabilized intermediates. The trick now is that since we have 2 different resonance structures, we need to go forward with both of those resonance structures if we're going to predict the possible products of this reaction. So let's go ahead onward to step 2 of our mechanism. And in step 2, what we will do is take those 2 different resonance forms and we will have the nucleophile attack each of those. So in the second step, the nucleophile attacks the electrophilic carbocation Opposites attract, of course, and this is completely analogous to what we saw in all of the other SN1 reaction mechanisms that we did so far, where we always had a carbocation being attacked by a nucleophile. So we'll go ahead and fill this in. So I'm going ahead and just drawing out my two resonance structures exactly like they were up top. Boom and boom, and we'll put our positive formal charge right here. So I've redrawn those two resonance structures. Now we need to ask ourselves, what is the nucleophile here? So we look back at what we have available, and remember that to be a nucleophile, we have to have pi bonds or lone pairs. We have a sulfur atom here. Sulfur is just below oxygen in the periodic table, so we'd expect it to behave very analogously. We're trying to look at trends here to help us in solving reactions. Trends are important. So sulfur has two sets of lone pair electrons, so we expect it to behave much like oxygen would in acting as a nucleophile. So we do our CH3SH, our methane thiol there, and I'll also redraw it down here to show that it can also attack the other resonance structure. So we'll go ahead and remember, opposites attracting, electrons are drawn to the positively charged carbocation, so we bring it over. Use the arrowhead to indicate its destination is that carbocation carbon to make a covalent bond between the sulfur and the carbocation. Same thing down here, sulfur lone pair comes over, bam, lands right on that carbocation to make a new covalent bond here in our electron pushing arrow map. So we'll go ahead and we will draw the products that result from this. Let's go ahead, and I'm not showing stereochemistry at the moment. We will fill in some wedges and dashes later on. So go ahead and fill this in. The sulfur atom, one of those two sets of lone pairs became the covalent bond, connecting the sulfur atom to the allylic carbon right there in red bond. We also had another set of lone pair electrons we haven't done anything to, so I'm going to leave that right there. If we calculate the formal charge on the sulfur atom, we're going to come up with a +1 formal charge. And we know there had to be a positive formal charge somewhere in there because our reactants for this step had a net charge of +1, so therefore our product of this step have to have a net charge of +1 as well. And then we come down here and we're going to do the same sort of thing, plug on our sulfur atom. And I'm going to go ahead and show that bond connecting to the sulfur in red. For emphasis, that's what was born through the electron pushing arrow that we showed, connecting the sulfur to the allylic carbocation. That sulfur is still bonded to a hydrogen, and it's still bonded to a CH3, so it's all about keeping track of who's where here. And we still have a set of lone pair electrons that are residing on the sulfur. That's going to result in that sulfur having a positive formal charge. So now we have our two intermediates resulting from the attack of the nucleophile sulfur on the electrophilic carbocation. Onward to step 3 here, our final step of the reaction mechanism. Just like what we've seen with all of the nucleophilic substitution reactions so far, when we yield an intermediate that has a formal charge somewhere on that organic compound, we generally want to get rid of that formal charge of +1 by deprotonating. So if we can break a bond between hydrogen and a heteroatom, meaning an oxygen, a nitrogen, a sulfur, etc., we're going to go about doing that. So third step is what we call deprotonation. So that means we're going to break the bond between an oxygen, nitrogen, sulfur, etc., and a hydrogen in order to create a final organic product that has no formal charges in it. So a stable final organic product, in other words. So we're going to take those two intermediates that we created as a result of step 2. I'm just going to redraw each of those so that we can show the deprotonation step taking place now to finish off this reaction mechanism. And at this point, the mechanism should be looking super duper similar to mechanisms that you saw previously for doing SN1 reactions. So you've seen at least a couple examples of SN1 reaction mechanisms before. We're just following up on that here. The game is going to be the same as it has been all along. Okay, so I think now I have taken those two structures up top that resulted from step 2 and just redrawn them. Everything looks good. Always a good idea to double check that you've got the right number of atoms in place in the right positions. So now onward to the deprotonation step, we need something that can act as a base in order to remove that proton, breaking the sulfur proton bond, the sulfur hydrogen bond. Generally, it's going to be the nucleophile that can do double duty here, serving as both the nucleophile to attack the carbon atom at step 2 and as our base here at step 3 to grab a proton, because by definition the base is going to have a lone pair of electrons or a pi bond that enables it to grab hold of a proton. So we'll use our thiol as our base. It's going to come over, use its lone pair of electrons to act as a base and grab that proton from the organic molecule, which is acting as an acid, break the sulfur hydrogen bond. The electrons from that sulfur hydrogen bond go onto the sulfur, and voila, we are off to the final product here. I'll do the arrows down here as well. Sulfur comes over, uses its lone pair of electrons to be a base. It's defined as a base because it's grabbing a proton, break the sulfur hydrogen bond, and we are on to drawing the final products of this reaction. So we're going to end up with 2 different constitutional isomers as a result of the reaction that we're doing here, because of the fact that we had that resonance step going on. So we had 2 different carbocation intermediates due to resonance, and therefore we're going to end up with 2 different constitutional isomer products here. So one of those is what I just drew up top, the product of those electron pushing arrows. The other is what I'm going to draw right here. So I'm just drawing this out, put my 2 sets of lone pairs on the sulfur, then go ahead and plug in my carbon chain here, and don't forget the carbon-carbon double bond in there. And here we go. So one thing to ask yourself at the end of these processes is whether you've actually made 2 different constitutional isomers here in the red box, or whether you have simply redrawn the same thing twice. So the way that we can tell that is whether we have changed the skeleton of the molecule in any way. Have we moved any atoms in going from the structure on top to the structure on bottom, or have we simply rotated the molecule around? So we can look at the carbon-carbon double bond, and in the structure on top, the carbon-carbon double bond is here at the very end, between carbons 1 and 2 is one way we could look at that. Whereas here, our carbon-carbon double bond is no longer at the very end of the molecule. Instead, it's more toward the center of the molecule. So yes, indeed, these are 2 different constitutional isomers because the double bond and the associated hydrogens are not in the same position in going from one constitutional isomer to the other. We've moved atoms around and hence electrons around as well. So these are constitutional isomers. The other issue we can look at here and deal with is the concept of the stereochemistry of the reaction. So you will notice here at the top, we started off with a chiral carbon bonded to the leaving group right there. And then we did our rate determining step, our slowest step of the mechanism to make a carbocation. Remember that the carbocation is a trigonal planar structure at that carbon, and therefore the bond that forms to that carbon will form from either the top face or the bottom face of the molecule, giving way to a mixture of the R and S chiral centers at that location. So therefore, as we look at our structures here, at step 2, we can highlight here that right here, where we're making that new bond to sulfur, we're going to expect the outcome of that to be a mixture of the R and S chiralities. So that location corresponds to right here in our product. So we expect that to be a mixture of the 2 possibilities, R and S, in other words, a wedge or a dash, in relatively equal quantities there. We come down to the other intermediate, the other resonance structure right here, and you'll notice that this carbon is a CH2 group, and that carbon that's a CH2 group is what's forming the bond to the sulfur, and that is not going to be a chiral carbon, and so therefore there is no R or S there because that is achiral. So then we go on to the next step here. The deprotonation isn't going to impact the stereochemistry because we're just removing a proton, not creating or manipulating any chiral centers. So then we come to our final product here, and if we're asked to provide the stereochemistry of the reaction, that is the RS stereochemistry, then we need to take a look at our carbon atom right here. That was the chiral center that resulted from the intermediate on top at step number 2. So it resulted from the intermediate that I'm putting in the blue box here. Went along with this guy down here. So we need to show that guy at the bottom as the structure and as the enantiomer of that. So go ahead and do that. And rather than a wedge, I'm going to show a dash. So we're showing the 2 possible stereoisomers there by manipulating the chiral carbon from R to S or vice versa. The other thing that can go on here is that due to the fact that our resonance structures are moving that pi bond from one location to another, the cis-trans stereochemistry can be scrambled as well. And so as we look at our structure up top in our product, if we look at the alkene group here, it's at the end of the molecule. So it has 2 hydrogen atoms here and here. And it doesn't matter which hydrogen you put on top or which hydrogen you put on bottom, they're going to be the same structure one way or the other. In other words, there is no cis or trans possible for this top set of 2 molecules. On the other hand, when we come down to the bottom here, this alkene group was the alkene group that was mobilized by resonance. And so we can actually show that as either the cis or the trans, and both of those will be present in the reaction mixture. So go ahead and plug this in. And we had currently shown it as the cis bond. Now we're going to show it as trans. And remember that we show it as cis to start with. We define it as cis because we're going down from the carbon atom to get further on in the chain here, and we're going down from the carbon atom to get further in the chain here. So that would be referred to as cis. On the other hand, from here, we go down from one carbon and up from the other carbon of the alkene group. Therefore, this is referred to as trans. But certainly the cis and the trans diastereomers would both form as a result of the reaction because of the fact that when we do that resonance, we're not going to be able to maintain the specific cis-trans that we started off with during this process. So this is one reaction that highlights how we can start with, in chemical reactions, one stereoisomer starting material. In this case, that's our stereoisomer up top here, highlighted in blue. And then once we do the reaction, we actually end up with 4 different products that represent a mixture of stereoisomers and constitutional isomers of one another. And this is really important in the area of drug discovery, particularly this issue of reactions not being stereoselective, reactions yielding multiple stereoisomer products, because stereoisomers are typically going to have different biological effects. The R and the S enantiomer, for example, one of them could be the blockbuster cure for a disease, one of them could be completely lethal. And so one challenge that scientists face in the world of organic synthesis is how to handle these situations where we start with a single reactant, we're interested in making a single product, but we actually end up with a mixture of different constitutional and or stereoisomers. And stereoisomers can, in many situations, be really difficult to separate from one another. And so that creates a challenge. And another challenge is that if one is thinking of how they can make a drug using the most profitable strategy possible, if they have to throw away 3/4 of their reaction product because only one of these 4 structures is the one that's of interest, that is a huge cost to them because they're throwing away a bunch of the material. So there's a lot of interest in developing strategies for reactions that are stereoselective, where we can predict accurately and tailor reactions to make specific stereoisomer products that are of use to us.